Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. We will continue today with the topic evaporation and concentration. So, in the last class we have seen that how we can design the single effect evaporator and we can calculate the steam economy and heat transfer area or heat exchanger area. Today we will continue with the design of multiple effect evaporator also, but before going into that we will just look into a few cases where evaporator is used effectively. So, first is the biological material, which is very heat sensitive material, and for them we use often evaporator to make them concentrated, for example milk, fruit juices, etc. So, these materials they contain fine particles and suspended matter in the solution. Okay. And what happened that during evaporation sometime those material can be deposited in the surface of the liquid side, and if they are not cleaned properly then maybe bacterial growth can generate and the contamination will be high. So, the equipment, the evaporator should be designed in such a way proper cleaning can be done. Okay. So, all this biological material that we are talking about, they exhibit a small boiling point rise when concentrated, okay, because they have the suspended solids in the finely dispersed form or have the large molecules that are dissolve. Okay. So, they generally provide a very less rise in the boiling point, because their nature is not like sodium hydroxide solution or NaCl solution like that. So, the amount of degradation of biological material during evaporation, that is basically a function of temperature and length of the time. So, we have to design in such a way so that the heat sensitive material does not expose to the temperature for a longer time. Okay. So, we will design or we will take the heat transfer area a smaller one. Okay. So, that way we can design them, and another thing we can do is to reduce the temperature. We can operate the evaporator chamber under vacuum, okay, so that the boiling point will come down. So, another one case is we can operate under vacuum, another is we can keep the time of contact low. So, we can see few equipments that is used for biological material. One is long tube vertical evaporator, that is specifically used for the condensed milk. Okay. So, so the reason is when we use this long tube vertical evaporators, so as they become concentrated, as they come down they will become concentrated. So, heat transfer will be difficult. Okay. So, and because they are high viscosity, mobility is also a problem. That is why we use the long tube vertical evaporator for them. Then there is falling film evaporator. These are mostly used for the fruit juices. Agitated film evaporator, those are used for antibiotics, fruit juices and gelatin also, because all these cases we need a continuous agitation to increase the heat transfer, because towards the end of evaporation as they become concentrated they may stick to the surface and reduce the heat transfer coefficient. There is also heat pump cycle evaporator for fruit juice, milk and pharmaceuticals, because these are very heat sensitive materials. So, they they are utilized by the heat pump cycle evaporator method. Natural circulation type short tube evaporator, these are used for sugar solution. Now, we will discuss the design of multiple effect evaporator. Let us first see the configuration of multiple effect evaporator. So, here we are considering 3 effect, okay, triple effect evaporator, and here this is forward feed evaporator, forward feed triple effect evaporator. So, this is the first effect, okay, this is the second one, and this is the third effect. So, we can observe that first in the first effect feed is entering, the mass flow rate of the feed is mf dot, xf is the concentration of solid in the feed stream, Tf is the temperature of feed, and that is entering in the first effect. Okay. So, in the first effect temperature is T1, this is the saturation vapor temperature or boiling temperature at the pressure. Let us say if the pressure is P1 in the first effect, okay, and here one side of the heat exchange surface this feed is there, okay, and the other side there is steam. So, this is the heat transfer area across which this heat transfer is taking place, where the overall heat transfer coefficient including the steam side and the material or the conductive material or the surface through which this heat exchange is taking place. So, the conductivity of that material and the convective heat transfer in the liquid side. So, together we have calculated this U1, okay, and Ms dot is the mass flow rate of the steam that is entering at a temperature Ts. Now, the steam is condensed here, okay, going out by this stream, and whatever evaporation takes place in the first effect, that is causing this vapor flow rate mv1 dot from the first effect, and that is coming out from the first effect entering into the second one, whereas the concentrated feed or concentrated liquid that is coming out by the evaporation of feed, that is going to enter to the next effect. Okay. So, what is happening in the next effect, as we have discussed that the pressure in the first effect is higher than that is in the second one, and eventually the second one the pressure is higher than the third one. Okay. So, to the high pressure side, from the high pressure to the low pressure we are sending the feed. So, no requirement of pump is there. So, feed is going from first to the second effect, and again from the concentrated liquid which is coming from the second effect is going to enter into the third one. From the third we are finally getting the product, okay, which is very high in the concentration of the solid, that is Xp, and coming out at a temperature T3. So, T3 is the temperature that is with respect to the pressure P3 in the chamber, and again T2 is the temperature which is prevailing in the second effect corresponding to the pressure P2. mv2 is the vapor that is generated in the second effect, and that is utilized in the third effect for heat exchange with the input stream or input feed which is entering from the second effect to the third one. This vapor which is generated in the third effect finally goes to the condenser, Okay. So, this is the total system. So, eventually this x f, which is the concentration of solid in the feed, will be concentrated in the x f 1, further concentrated in x f 2, and we are getting product x p, that is highly concentrated. So, utilizing the same steam m s dot, we are now generating vapor m v 1, then m v 2 and m v 3 dot. So, m v 1 dot, m v 2 dot and m v 3 dot. So, we can see that how we are increasing the steam economy as well, and in more general cases we consider that these three effects are equal in size, that is the heat transfer area available are same, and that is in most of the cases design criteria for the iteration that we perform, that when this area are almost close to each other or within a variation of 10%, we shall stop further iteration. Okay. So, that will be our final design of the multiple effect evaporator. Now, let us see how we can step by step perform the overall balance, solid balance, enthalpy balance, and finally design the system. Okay. So, there are few design steps, we will follow them one by one. First is use the overall component balance to completely determine the feeds and product streams. These numbers are fixed and are not changed by iteration. So, obviously, numbers will be fixed of the in feed and the product streams, because you know the number of effect that you are going to design. If it is a 3 effect system, so one feed stream is entering, one concentrate from the first, another from the second, and lastly from the third. So, 3 concentrated streams are coming out, and similarly the vapor V 1, V 2 and V 3. Okay. So, those are not going to change through the whole system. I mean their number does not change, but value may change as you perform iteration one after the other. Okay. So, calculate the total amount of vapor vaporized. So, that is V total, that is V 1 plus V 2 plus V 3. V 1 the vapor you are getting in the first effect, V 2 in the second effect and V 3 in the third effect. And normally we consider that equal amount of vapor is generated, that is V 1 equal to V 2 equal to V 3. Then use component and material balance to get estimates for the remaining flow rates within the system and the composition of the intermediate streams. Okay. So, what we are doing in the third step, that is component and material balance. Okay. Component and material balance to get estimate from the remaining flow rates within the system and the composition of the intermediate stream. That means, we need to know the fraction of the solid in the streams that is coming out, and that can be done by the component balance and the overall material balance. And once we get the concentration, we know that concentration has a relation with boiling point rise. Okay. Although the biological material we have seen that they does not provide very high boiling point rise, but to identify how much amount of elevation is there, or to understand how boiling point elevation affect the situation, affect the operation in a multiple effect evaporator, we will solve now including boiling point rise. However small the value may be, because that will help you in designing a system where actually there exists a significant amount of boiling point elevation, right. So, from the known outlet concentration and pressure in the last effect determine the boiling point in the last effect. Then determine the overall temperature drop between the steam and the saturation temperature of the last effect. Okay. So, total delta T that we are getting in case of a triple effect evaporator, that will be T s minus T 3 minus boiling point elevation. So, if you want to understand that how this is generating, so we know that T s is the steam that is entering in the first effect, temperature of the steam that is entering in the first effect. Now, the boiling point in the first effect corresponding to, let us say, pressure T p 1 is T 1. So, in the first effect we are getting this much delta T. Now, this T 1, the vapor is coming out at this T 1 temperature only, and that is going to enter into the second effect as steam. Okay. So, in the second effect we are getting T 1 minus T 2, okay, where T 2 is the boiling point temperature corresponding to pressure P 2 in the second effect. Now, this steam that is coming out at T 2, this vapor that is coming out will enter into the third effect. Okay. So, in the third effect we are finally getting T 2 minus T 3, that is we are getting T s minus T 3 when there is no boiling point elevation. Now, if boiling point elevation happens or it occurs, then in the first effect, okay, in the first effect what will be the concentration, because of that some boiling point elevation will be there. Similarly, in the third effect as well and in the fourth effect as well. Okay. So, when T 1 comes out, it includes that boiling point elevation, but when it enters in the next effect, okay, so in the next effect the effect of the elevation is not there. So, that we can't consider there. That's why what we do, that the total difference will be total delta T that we can get when the boiling point rise exists will be T s minus T 3 minus delta, or let us say I can write boiling point rise in 1 plus boiling point rise in 2 plus boiling point rise in 3. Okay. So, this is coming because when boiling point rise will exist, here it will be T 1 that is getting in the first effect, that will include minus B P R 1. Here also we will get T 2 minus B P R 2, and in the T 3 also we will getting minus B P R 3, right. So, all together we can take as T s minus T 3 minus summation of all the boiling point rise that has occurred in the system in all the 3 effects, right. So, this is how we can calculate the total delta T available. Okay. So, T s and T 3, it is already defined. Then allocate the overall drop among the various effects since the areas are the same. So, we will consider, as I said, that this will be a design consideration, that all the areas of the 3 effect will be same. So, the temperature difference in each effect is roughly inversely proportional to the overall transfer coefficients. Okay. So, u1 delta T1 equal to u2 delta T2, that is equal to u3 delta T3. So, u1, u2, u3 are the overall heat transfer coefficient in the first, second and third effect, and delta T1, delta T2 and delta T3 are the temperature difference in all the 3 effect respectively. Okay. So, definitely since the temperature of steam that is being entered and the pressure that is inside the chamber all are different. So, u1, u2, u3 will be different. However, the temperature difference in each effect is roughly inversely proportional to the overall transfer coefficient. Okay. So, that means we can write here as delta T1 if we want to calculate delta T1. Okay. So, that will be equal to summation of delta T into 1 by u1 divided by 1 by u1 plus 1 by u2 plus 1 by u3. Okay. So, use the delta T and boiling point rise values to obtain estimate of all the temperatures in the system, and we can start with the steam entering in the first effect, right. So, if you think about that how we can derive this, you can calculate like this, that if we identify the effect, if we identify the total effect, that is actually because this is equal amount of heat transfer is taking place, where in all the effect. Okay. So, what we can write is T s minus T1, okay, because Q that is equal to U A delta T, right. So, here we can write that Q that is equal to U1, that is in the first effect, okay, into A1 into the temperature difference in the first effect, T S1 T S1 minus T1. Okay. So, if I can write T s minus T1, that is equal to Q by U1 A1. Okay. Similarly, T1 minus T2, that is equal to Q by U2 A2, and T2 minus T3, that is equal to T2 minus T3, that is equal to Q divided by U3 by A3, right. So, if we add now all this equation, all the 3 equations, so we are getting T s minus T1, that is the overall heat transfer. So, Q will be equal to overall delta T into U into A. Okay. So, that is equal to, since Q by A is same, we can write 1 by u1 plus 1 by u2 plus 1 by u3. Right. So, that means if q equal to this one, okay, Ts minus Ts minus T1 UA. So, this we have add all them and then we are getting this. So, here we can take QA in this side because the area is same. So, finally we are getting delta T into U, that is equal to 1 by U1 okay, 1 by U1 plus 1 by U2 plus 1 by U3, right. So, okay. So, what we have done is here we have added all this temperature to find the total area, that is Q equal to UA delta T. So, total area UA delta T is coming equal to all this summation of all the overall heat transfer coefficient. Okay. Now, if we want to calculate this any any temperature drop, so that will be summation of delta T into 1 by this, I mean any effect that divided by 1 by U1 plus 1 by U2 plus 1 by U3 into overall heat transfer coefficient of any effect that we are interested in. Okay. So, if there is boiling point elevation exists, so we can calculate this T1 equal to Ts1 minus delta T1. Similarly, T2, that is equal to T1 minus boiling point elevation minus this, because T1, that is the temperature at which this vapor came out, okay, but that has included this boiling point rise in that first effect. So, we are taking that minus, then Ts2 will be what? T1 minus boiling point rise in the first effect. So, this is the steam actually that is entering in the, this is the okay, this is the temperature of the vapor entering in the second effect. Okay. Similarly, Ts3 which is entering effect if in the third effect, the temperature of the steam which is entering in the third effect, right. And T2 will be equal to T1 minus boiling point rise minus delta T2. So, this T2 which is the temperature in the second effect, T3 which is the temperature in the third effect. Okay. And yes, so T1, T2, T3, these are the saturation temperature for the effect 1, 2, 3, and Ts1, Ts2, Ts3, these are the temperature of condensate leaving the effect 1, 2 and 3. So, Ts1, this is the condensate that is leaving the first effect, Ts2 which is leaving the second effect, and Ts3 which is the condensate which is leaving the third effect. Now, solve the set of equation that is made up of one enthalpy balance for each effect, okay. Then check whether the V1, V2, V3 are close to each other, and then we can have the new values. If they are not each other, the iteration will goes on. Finally, we will solve for heat transfer rate and area in each effect. So, we will calculate that Q1, that is equal to S into lambda S1, and A1 that is equal to Q1 by U1 delta T1, similarly A2 and A3. So, lambda S is latent heat of vaporization, steam at that temperature where it is entering minus the liquid enthalpy at that temperature. Again we will compare the area and find that they are close to each other or not. So, then the new delta T that we will take, so that will be delta T into A1 by A mean, and similarly we will calculate delta T2 and delta T3, because see delta T1 surface area will be proportional to heat transfer. I mean, if the area is higher, so higher amount of heat transfer will be there, and since we have we can calculate that delta T1 in that is the change of temperature in the first effect proportional to the area. And finally, the capacity of the multiple effect evaporator will be Q, that is equal to Q1 plus Q2 plus Q3, because the total heat transfer we are getting in the system in the first, second and third effect. So, that is why we will add them together. So, just quickly I will discuss a problem, that is a triple effect forward feed evaporator is being used to evaporate sugar solution having 10 weight % solid to a concentrated solid of 50%. Boiling point rise is governed by this equation, where x is the fraction, weight fraction of the sugar in the solution. Saturated steam at 205.5 kilopascal, this is being used, that is entered in the first effect. Pressure in the vapor space of the third effect is given, that is 13.4. That means, corresponding to this we can calculate the temperature in the third effect. Feed rate is given, temperature is given, Cp is again by concentration equation is given, and U1, U2 and U3 this is given, U1, U2 and U3 is given. So, if each effect has the same surface area, calculate the area and the steam used and the steam economy. So, steps will be this way. First is pressure temperature in the last effect, because the pressure is given. So, temperature correspondingly we can calculate. Then is overall balance to find the vapor and the liquid content, overall balance to find the vapor and liquid content. Okay. So, then solid balance to find the concentration in each effect. From the concentration we can calculate boiling point rise and temperature drop. Finally, calculate the specific heat and from that enthalpy. From the heat balance we can find out actual V, S and L and check with what we have assumed. Then calculate the total heat transfer area of the evaporator, and if we are getting within 10% variation we will stop, otherwise the iteration will continue. Okay. So, first in 13.4 kilopascal saturation temperature we have calculated. So, the saturation temperature from the steam table is coming 51.67, and the from the steam table we have calculated this. Now, equation for the boiling point rise in the effect 3, where the concentration of weight fraction given is 0.5. So, we will find the boiling point rise in the third effect, right, using that concentration formula. So, we have added that T3, we are getting now T3. Then we are making an overall balance. So, total feed will be divided into L3, that is the product we are getting, plus V1, V2, V3, that is the evaporation occurred from the evaporator. So, by doing the balance of the solid concentration, we are getting what is the amount of L3, right. So, F into XF, that is L3 into 0.5 plus V1 plus V2 plus V3 into 0. So, we are getting L3 putting into L3 we are calculating V and taking equal V in all the cases. So, we are getting 6048 kg per hour. This is the system. So, third effect we have calculated this L3 and this is the forward feed evaporator. Okay. So, we have calculated we need to calculate TS3, TS2 and TS1. We have calculated T3, now we will calculate T2 and T1. How? Because we need to identify the boiling point elevation in all the effect. So, we will first calculate what is L1 and do the balance on L1. Okay. So, L1 V1 plus L1 equal to 6048 plus L1, L1 is this one. Now, again using that L1 value, L1 is equal to V1 plus L2. So, we will calculate L2 and then again using L2, this will be L1 and this will be L2. So, using that we can calculate so this is V3 and L3. So, we can calculate L3 is equal to 4536 kg per hour. Now, making a solid balance on the effect 1, 2 and 3 and solving for x. Okay. So, x we will calculate first. Okay. So, in the first effect 22680 into 0.1, this is the solid, that is L1 x1, that will be this L1 that we are getting 16632 into x1. So, x1 is 0.136. Similarly, x2 is 0.214 and x3 is 0.500. So, boiling point rise we will use in this equation to find the boiling point rise in each effect, okay, 1, 2 and 3. And finally, delta T available that we are getting, that will be Ts1 saturation temperature of the steam entering in the first effect minus T3 that is saturation temperature minus all 3 boiling point rise. So, then we know that delta T1 that is temperature rise in temperature difference in the first effect will be summation delta T 1 by U1 by 1 by U1 plus 1 by U2 plus 1 by U3. All these are given values. So, similarly, delta T1, delta T2 and delta T3 we will calculate. Okay. So, to calculate the boiling point of the solution in each effect, so T1 that will be equal to Ts1 minus delta T1, because Ts1 at which the liquid has condensate because of the boiling point elevation. So, T1 will be Ts1 minus delta T1. So, 121.1 minus 15.56, that is equal to 105.54. Now, how we have calculated here 15.56, because here 12.4, 19.5 and delta T3 has come 34.07. However, we have considered this after first trial that the temperature higher amount of difference we are getting in the first effect. So, that is why we have increased this a bit proportionately and reduced the other temperature drop in the delta T2 and delta T3. So, here T1 is 105.54. Okay. Similarly, T2 we have calculated, T2 was T1 minus boiling point rise minus delta T2, and that we are getting 86.84. So, T2 is 86.84 and Ts2 will be, that is the condensate from the second effect will be T1, that means what is entered minus BPR1 boiling point rise. So, that we are getting 105.18. Similarly, for the third effect we have calculated that T2 that is entered minus boiling point rise minus delta T3, that is the difference in the third effect. So, T3 we are getting 54.12. So, T3 that will be that 86.84 minus boiling point elevation. So, 86.19. The temperature in the 3 effect now we have calculated. So, Ts1 that the steam has entered, T1 the vapor that has gone to the next effect, as Ts2. So, it has been reduced because the boiling point elevation has been deducted. Then T2, the effect temperature in the second one, that is going as T3, again boiling point rise has been removed from this value, and similarly for the third one. So, heat capacity again formula is given. So, all the heat capacity we will calculate and will use that 0 datum temperature to make all the heat balance in the first effect, second effect and third effect. So, in the first effect H1, that is the enthalpy, that is equal to HS2 saturation enthalpy at TS2 plus 1.884 into the boiling point rise, because it has become superheated. So, that will include. Okay. So, H1 we have calculated. So, lambda S1 will be HS1, that is the vapor saturation enthalpy, minus HS1, that is the liquid enthalpy. Okay. Effect 2 we are getting 86.84, that is T2, Ts3 is 86.19, boiling point rise is 0.65. So, H2, that is enthalpy, will be the saturation enthalpy plus the because of the boiling point rise 1.884 into 0.65. So, that is H2, the steam that is entering. Again lambda S2 that we have calculated in the second effect. So, like this heat transfer in all such effect we have calculated, and using that enthalpy, finally we can calculate that V1, V2, V3, that all the effect what we are getting, right. So, this way, doing the overall balance, solid balance and enthalpy balance, we can calculate the total vapor that is generated and also calculate the total heat transfer area. Okay. So, once we got all the values of stream, okay, we can calculate the Q1, Q2, Q3, that is the heat transfer, and find out the area A1, A2, A3. Okay. So, if the area are almost equal within the 10% variation, our iteration stops here. So, thank you. We will stop here.